Hi, everybody. So now we're going to just start a discussion of a family of groups that you can construct out of matrices. And these are really fundamental and actually lead into a whole other branch of group theory called Lie theory, which is extremely important in physics and in geometry and lots of other differential equations, lots of other branches of math. And so we're going to start with a quick review of linear algebra. Then we're going to talk about some of these important matrix groups. And then at the end, talk a little bit about the implications of this work for Euclidean symmetry in the plane. So let's get started. So I'm not going to go through all of linear algebra, but I just want to remind you of a few things, some fundamental definitions and properties. So the most fundamental definition is the definition of a linear map. And I'm just going to stick to Rn and Rm. So a map from Rn to Rm is linear if it changes sums to sums and if you can factor out scalar multiples. Just as a side remark, this property that f of x plus y equals f of x plus f of y should look familiar. It says that if you just think about Rn and Rm as additive groups, a linear map is a homomorphism. But it has this additional property that if you have a scalar and you multiply an element by a scalar, you can pull out the scalar. So in some sense, a linear map is a group homomorphism plus a little bit extra. And if you've learned about vector spaces, a vector space is an abelian group with some extra structure. Okay, now one sort of way to visualize or make linear maps concrete is to think of them as matrices. And if you have a linear map from Rn to Rm, you can represent that as an m by n matrix. So notice that the m and the n are reversed. That's because I like to think of my vectors as column vectors. And so the way you do this is if you have an m by n matrix A, and you think of your element x in Rn as a column vector, which is how I always like to do it, then you can multiply A times x. And since this is m by n, and this is n by 1, the result is an m by 1 column vector in Rm. And this is linear just because it's matrix multiplication. So A times x plus y is ax plus ay, and A times, let's say, cx, where c is a scalar, is the same as c times ax. So some standard examples, the identity map. So you have the identity map from Rn to Rn, and the associated matrix is the identity matrix, which is a square matrix. It's n by n, and it has ones down the diagonal and zeros in the off-diagonal entries. And of course, there's the zero map. That's a linear map. That's the function from Rn to Rm, which has the property that f of x is just 0 for all x. And it's represented by the zero matrix. The m by n zero matrix. And then maybe just one more example that we've also seen, which is if you take, if theta is a real number, and you take the 2 by 2 matrix, cosine theta minus sine theta, cosine theta, this gives a rotation of the plane. And you can see that because if you take the vector 1, 0, which in some places is called I, and you multiply by m of theta, you get, so you get cosine theta, sine theta, and m of theta times 0, 1 is minus sine theta, cosine theta. And if you think about what's going on here, here's 1, 0, it's I, and it goes to the vector where, I mean, you can think of this here as cosine theta I plus sine theta j. Here's j over here. And so we've rotated it by an angle theta. And similarly, the vector j gets rotated over to here by an angle theta. And these remain perpendicular to one another. We've seen this map in various forms from one place to another. So, I guess the message to think about is that a rigid rotation of the plane is linear. And in fact, a rigid rotation of 3-space or n-dimensional space is also a linear map. Okay. You have an abstract notion of a linear map, and you have a concrete notion in terms of a matrix. These are the same. In other words, every linear map that you can think of can be written in this form, multiplication by a matrix. And the way you do this is you take the standard basis vectors for Rn. So that's these EJs. So EJ looks like it has a bunch of zeros. It's an element of Rn, by the way. So it has n entries, and it has a 1 somewhere in the middle, position j, and the rest of them are zeros. And you also have f's, and they're in Rm, and they look exactly the same, except they only have n entries, and they have a 1 in position I. And if you apply the map, if you have an abstract linear map T, and you apply it to the vector EJ, the result has to be a sum of the FIs. I mean, because if T of EJ, let's say, is x1 down to xm, it's an element of Rm, then this is the same as x1 f1 plus x2 f2 plus xm fm. And if we write this in the following way, from I goes from 1 to m, aij fi, so notice the index here matches the index there, and the index here, j, tells us which j we applied to. And if we do this for j equals 1 up to n, then we actually get a matrix whose entries are the aij. And if you sort of write this out a little bit, and we just focus our attention on the jth column, the jth column has A1j, A2j, all the way down to AMJ. And when you multiply that times EJ, which remember just has a 1 in position j, then in this matrix multiplication, these zeros here mean that none of these columns do anything. They all get hit by 0. And similarly, all of these columns get hit by 0. And the only column that matters is the jth column. And as a result, you get the answer A1j down to AMJ, which is what so this is in fact what we were supposed to get. This is T of EJ. So presumably you went through this in detail in linear algebra. I just want to remind you that the rule for converting a linear map to a matrix, at least with my conventions, is you take the standard basis vectors of your Rn, you apply T to it, and the resulting coefficients form columns of the associated matrix. And then if you do it that way, then matrix multiplication by column vectors gives you back your linear map. So, I mean, if you really want to sort of drive this home, if A of E1 were 2f1 plus f3, and A of E2 were 5f1, sorry, f2, not f3, minus 6f2, then the associated matrix would be, you take 2 and 1 as your first column, and 5 and minus 6 as your second column. And then you can check that if you multiply, if you let this be A, that AE1 means A times 1, 0, which is going to be, in fact, 2, 1, which is, in fact, 2f1 plus f2 as it's supposed to be, and so on. And the key point about this construction and the reason matrix multiplication is defined the way it is because if you have a pair of linear maps, and this, by the way, should be VT. So you have a map T which goes from Rn to Rm, and a map V which goes to Rm to Rp. Then the composition V composed with T is a map from, first you do T, so you go from Rn to Rm, and then you do V, so you go to Rp. So there's a matrix. Let's suppose that A is the matrix associated to T, and it's going to be an M by N matrix. And B is the matrix associated to V, and it's going to be a P by M matrix. And I guess the great thing, or the reason matrix multiplication is defined in the way it is because then you should have a matrix associated to V composed with T. That should be a P by N matrix. And in fact, if you take B times A, you're going to get a P by N matrix. And notice that B corresponds here to V, and A corresponds here to T. So the matrix associated to the composition of two linear maps is the product of the associated matrices. How do you see this? Well, it depends on how good you are kind of with index calculations. We could just take a quick look at this. So remember that the matrix A, right? A corresponds to T. Its entries are given by, you take T of EJ, and you get the sum of AIJ FI as I goes from 1 to M. And this is what's true for J goes from 1 to N. So the EJs are a basis for Rn, the F are the basis for Rm, and we need one more letter. So let's let T sub k, for k equals 1 to p, be the vectors that give the basis for this Rp. And we know that V of, so now V goes from Rm to Rp, so V of Fi should be the sum of, let's call it, the matrix associated to V is B, so that's going to be B Ki Tk as k goes from 1 to p. And if you take the composition VTEJ, that's V of the sum from 1 to M AIJFI, which is the sum by linearity. We can move the vector V through the sum, and then we can make this substitution, and we get AIJ BKI T sub k. There's a sum in here. K goes from 1 to p. And we can regroup this here and reorder the sum and write it as the sum as k goes from 1 to p. The sum is, I guess it's Ji goes from 1 to m. A BKI AIJ TK. And now if you finally go back to the definition of the way matrix multiplication works, you see that these right here are, on the one hand, the entries in the columns of the matrix associated to VT, but on the other hand, they're also the thing you would compute if you took the matrix product. So this is, if we call this, here we have a J and here we have a K, so let's call this CKJ. And if we define a new matrix C by the rule that the entry CKJ is the sum I goes from 1 to M, BKI aij, this rule means that C is the matrix B times the matrix A. So matrix multiplication corresponds to composition of linear maps. And I went through this because this is such a fundamental thing that I think it's worth reminding everybody of why this is true and that it is true. And then there's two more facts which I'm going to say less about, but which I hope you remember from linear algebra. The first is that if you happen to have a linear map which is bijective, then its inverse is also linear. And the way you see that is its inverse map is given by the inverse matrix. And conversely, if you have a linear map which corresponds to a matrix and the matrix is invertible, then the map is bijective. So I meant to say here linear. In particular, the inverse of a bijective linear map is also linear. So, and you can test to see if a matrix is invertible by computing its determinant. And if you get a non-zero value, then you know that the matrix is invertible. So invertible linear maps or bijective linear maps, invertible matrices, and matrices with non-zero determinant these kind of all give, these are all the same, all correspond to the same thing. That is to say, invertible linear maps or bijective linear maps. Okay, that's the first part of what we need to remember from linear algebra. The second thing we need to remember from linear algebra is the dot product. And the dot product in Rn is just defined as the simpler kind of matrix multiplication, where if you have two vectors, you just multiply their corresponding coordinates together and add them up. So for instance, 3, 5 dotted with 2, 7 is 3 times 2 plus 5 times 7, which is 6 plus 35, which is 41. And this is also sometimes written this way. It's just a different notation, but you'll sometimes see both. So the dot product has a lot of properties, and I'm going to summarize them here. First of all, it's symmetric, or put another way, it's commutative, right? And that's just because if you take the sum of AI, BI, EI, and you dot it with the sum of BI, EI, which is the sum of AI, BI, it's pretty clear that it doesn't matter. If you reverse these, you would have the sum of BI, AI, and that would be the same. It's bilinear. So in this case, what that means is that if you take the dot product of, it basically means the distributive law holds. That is to say, if you take x and you dot it with y plus z, that's x dotted with y plus x dotted with z. And that's because this is going to be the sum of AI times BI plus CI, where x is the sum of AI, EI, y is the sum of BI, EI, and z is the sum of CI, EI. And then and that's just going to be by the distributive law, you can separate the sum. And also if you multiply, let's say, x by a, then you can pull it out, because that'll put an a in front of, ax dot y is just a times the sum of AI, BI. And because it's symmetric, let me just point out, I've written these things on the right and on the left, but it's true on the other side too. That is to say, x plus y dotted with z is xz plus yz. If you wanted to be fancy, you could say, look, x plus yz is the same as zx plus y, which by this property splits apart, and then you could reverse each term using symmetry. The other properties of the inner product are called its positive definite, and the positive means that the dot product of a vector with itself is always bigger than or equal to 0. And the definite means that the only time you get 0 is that if x is 0. And that's because the dot product of a vector with itself is the sum of AI squared. If x is the sum of AI, EI, then the dot product of x with itself is the sum of AI squared. And that's always positive. It's a sum of positive numbers. And the only way it can be 0 is if all the AIs are 0, in which case x is 0. And the place we tend to see the dot product is that it comes in when we measure the lengths of things. So the dot product of a vector with itself is called the norm of x, and it's the sum of the squares of the coefficients of the vector. Geometrically, you can think of it as the length of the vector by the Pythagorean theorem in n-dimensional space. But if here's your vector x, and here's a1, e1, and here's a2, e2, then the length of x squared is a1 squared plus a2 squared. And this is true in higher dimensions as well with more coordinates. And a little bit of a generalization of that is that you have the distance formula, even in Rn. If you have two vectors, the distance between the corresponding points is the length of the vector x minus y. So if this is x and this is y, the length of the vector x minus 1y squared is the squared distance from x to y. And that's a summary, I think, of the main facts that we're going to need from linear algebra. That matrices and linear maps correspond, invertible matrices have non-zero determinant and correspond to bijective linear maps, the dot product is bilinear and symmetric, and the norm measures Euclidean distance.